Jai Hind, one and all. The next topic which we are going to study is electric field intensity due to a infinitely thin plane sheet of charge. So we need to consider an infinitely thin plane sheet. So let us consider this is the infinitely thin plane sheet which is being kept. So it is infinitely long as well and the sheet is infinitely thin. Now the charges are uniformly distributed. Charges are uniformly distributed on it. Am I clear? Now suppose if we take this example, this is the sheet. Now the sheet has been kept like this. This is a two-dimensional board, as you can see. This is a three-dimensional sheet in the three-dimensional surface. In the three-dimensional 3D surface, we are watching it. So I have kept the sheet in this way. In this way, it will be, you will be observing only this part. You will be observing only this part of the sheet. Now the thing is, if we draw only this part of the sheet and the charges are uniformly distributed on this sheet, even over here, charges are uniformly distributed over the sheet. So if I draw this sheet over here like this again, this is the sheet, this is what you will see, okay? Charges are uniformly distributed on the sheet like this. So for a positive charge, we notice very clearly that the electric field lines are always radially outward. The electric field lines are always radially outward. It should be like this. So we got the electric field lines like this. Now in this electric field line, if we consider the line will be in the form of a cylinder, because the cylinder is a symmetric figure which will be distributed on both the sides. And the cross-sectional area of the cylinder will be carrying the minimum charge. The cross-sectional area of the cylinder will be carrying the minimum charge. That means if I draw a cylinder over here like this, a cylinder over here, it will be stretching like this. So we can draw this figure over here. We are having a circle. Into the surface, we are having a circle which will be carrying the minimum number of charges. And the cylinder will be piercing the sheet. Like this. This is how it will look like. Suppose this is the sheet we are having. And if we pierce this pen across this, then we can have like this. The pen will look like this. This is the sheet and this is the pen which will pierce through it. So the pen is a cylinder body, this pen is a cylindrical body and it will pierce through it. Now suppose if this pen is hollow inside, and if this plane sheet carrying the n number of charges, then this cross-section area will be carrying the charges which will go through this one. Am I clear? Now, this is the diagram we are having. So this is a surface, plane surface, this is the plane surface, again you can see, and this is the third surface we are having on the cylinder. In the previous diagram also we have seen this. Now since the charges are distributed uniformly on the sheet, the electric field lines is radially outward. The unit vector n, or you can say the area vector, is pointed in the same direction of the electric field. Electric field is pointed outward, unit vector n is always pointed outward, and in this upper region, in this upper curved region, the unit vector n will be in this direction. The unit vector n will be in this direction. Our objective is to find the electric field intensity at a point P. Let the point P lies at this point. This is the point P. At this point, we need to find the electric field intensity. This is point P where we need to find the electric field intensity. Let's draw a straight line actually. That's why I'm just erasing it. We need to draw a straight line like this. Okay? This is point P where we need to find the electric field intensity. Am I clear? Now again I will say that this sheet is so thin. This sheet is so thin that you can't even distinguish between this side and this side. The sheet is infinitely thin, infinitely long, that you can't distinguish about the first side and the second side. It will seem that it will be having a single side only, and the charges are uniformly distributed on it. Hence, the derivation goes like this. According to Gauss law, close integral E dot ds vector plus close integral E dot ds vector plus close integral E dot ds vector equals to Q upon epsilon naught. This is the first region. This is the second region. Let us suppose this is the third region. First region, second region and third region. So we can see E and unit vector n making an angle of 0 degree over here, 0 degree over here, but 90 degree. E over here and area vector n over here, they are making an angle of 90 degree. Hence, this region 2 will be equals to 0. And hence, we will be left with, if we convert this into a scalar form, we will be having E ds cos 0 degree, region 1, region 2, E ds cos 90 degree plus close integral E ds cos 0 degree, region 3 equals to Q upon epsilon naught, which will 2 E ds is equals to Q upon epsilon naught. It is very easy. This part is 1, this part is 1. 2 E ds equals to Q upon epsilon naught. This part is 0. So E is again constant. Let's take E as constant. Close integral E dot ds equals to Q upon epsilon naught. 2 E dot s is equals to. Now think, since the charges are distributed uniformly, where? On the surface. Charges are distributed on the surface. Hence, we have studied surface charge density. What we have studied? Surface charge density, and this is what? Q upon area, Q upon surface area equals to sigma. Sigma is the surface charge density. Therefore, we can write sigma into surface area equals to epsilon naught. In bracket, we can write Q upon surface area is equals to sigma. This S will get cancelled out, and E will be equals to sigma upon 2 epsilon naught. This is the outcome we are having. So always you remember that the sheet we have considered is infinitely thin, infinitely long. It is in such a way that we can't even distinguish between the first side and the second side. It will just seems like it is having only a single side. Charges are uniformly distributed on the sheet, and we have drawn a cylinder. Why cylinder? Because cylinder is a uniform surface, symmetric body. Suppose if we consider this whole cylinder from this point, this is the midpoint, okay, then this part is L and this part is L. So this is a symmetric body. The cylinder is a symmetric body. The area of cross section is symmetric in nature. Always do remember, area of cross section will remain symmetric in nature, and that's how the derivation goes on.